Thank you. Thank you very much. Thank to the organizers for inviting me here. I'm very happy to be here in spite of 24 hours of travel and the horrendous weather we had over lunch, which probably my voice will... I didn't coin the, nom is too generous. I didn't coin the term biolinguistics. I mean, I thought that was what it was. I mean, they had a seminar at MIT, Salvador Luria, Nobel Prize for Medicine, and Chomsky. They had a seminar with biologists and linguists. That was biolinguistics. So I think that's what it was. Now, the most important term in this title is this, steps. It's just the beginning of something. I'm going to tell you about ongoing research. And it's something that we think, David Medeiros, Juan Uriagereka, before he came at SAR in this university and was mostly doing, unfortunately, administrative work, we think we have opened a Pandora's box. New and new things come, once you have this approach, I will highlight very briefly to you. More and more things come up, and I have, every other, not really every other day, but every other week, David Medeiros comes to see me. He has found another application of this thing. And we have to stop him because he now has to finish his dissertation. He already defended. He has to finish and deposit this dissertation. I say, stop with this. Write down all you have done so far, and then you have a lifetime to continue. So we really think it's very productive. Now, this is a quote by the great Richard Feynman. Cedric Burks is very familiar with this. He said, when I was in high school, my physics teacher, whose name was Mr. Bader, called me down one day after physics class and said, you look bored. I want to tell you something interesting. Then he told me something that I found absolutely fascinating and have since then always found fascinating, the principle of least action. Really fascinating. So we are treading in the wake of the principle of least action ourselves. And again, Feynman, in his lectures on physics, something as a physicist I studied, Physics 101, some zillions of years ago, he says, now, in the further development of science, we want more than just a formula. First, we have an observation. Then we have the numbers that we measure. Then we have a law, which summarizes all the numbers. But the real glory of science is that we can find a way of thinking such that the law is evident. This is really beautifully said. My emphasis there. So this is the plan. First part, what is language? That you want to find the physics of. I don't have to tell you what language. I'll go very quickly on this. Second part, what is the physics we want to find for language? And then trying to put all this together. And then, time permitting, some lessons and conclusions. These are the third factors have been evoked here already today. Third factors in language design in Noam Chomsky's characterization, facts about language which are neither encoded in the particulars of our genome, nor learned from the environment, but determined by domain general principles beyond the organism. So something coming from physics and mathematics and criteria of optimal computation. I like this sentence because it was on the front page of the New York Times in 2009, and it happened to be published just when my friend and colleague Heidi Harley was putting together, as she has in the meantime, a software to create syntactic trees. So I say, okay, you have this program to generate syntactic trees. Why don't you draw the syntactic tree of this sentence? Top federal regulators say they were taken aback when they learned that a California congresswoman who had helped set up a meeting with bankers last year had family financial ties to a bank whose chief executive asked them for up to $50 million in special bailout funds. This is English, front page of the New York Times. Now, I think in the next days you will hear a lot about language evolution, and my suggestion, don't settle for anything less than this. Okay? Because one thing try to explain, and some probably will, try to explain, John kicked the ball. Maybe you can explain the origin of John kicked the ball. We want to explain the origin of this. This is a syntactic tree with 32 levels of embedding. You will not be surprised, and it could continue. You don't have to stop at 32. Because one can say, you will never going to believe me, but the New York Times says the top federal regulators, blah, 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 and you can continue and continue. We don't have to stop at 32 levels, so it's indefinite. Okay, it's 4 full pages in PDF. And why do we have such a structure? This is just the top of the syntactic tree. I don't have to remind you that there is a lot of repetition, of the same fundamental components, and then you have again and again and again and again the same structure, which is the X-bar structure. So what we want is the following. We want the syntactic dependency to remain as local as possible, and do not multiply in kind, and then we want the overall number of such dependencies to be minimized. But the syntactic structure must allow for further expansion, theoretically indefinitely so, under the constraints of preserving the structure itself. What we have here, as you will see, I hope in a moment, I'll show you self-similarity. So, the first basic strategy, all well known to all of you, is merge. You have elements that within a phrase belong together, and the most basic way of doing this is to form a set. The minimal set is 2 members only, so we form a set of 2. And then we continue doing this because we have phrases in a sentence also belong together. The most basic way of doing this is form another set, the minimal set, 2 members only. And then we have headedness or endocentricity. We do not want to multiply entities, especially kinds of entities, beyond necessity. So we treat the whole as being of the same nature, the same kind of entity as one of its members, and we do it again and again and again until the sentence is completed. And the strategy number 3 is locality. Not all members are equal. There are hierarchies. Familiar with C command, it doesn't much here matter how you exactly define C command. In what we are going to say, it can be the una sportish definition in terms of maximal thing, or it can be the previous definition. Make it as small as local as possible and continue doing this until the sentence is completed. And then you apply the same operation to the output of the previous one and keep doing this until the sentence is completed. What is the perfect solution to all this? Well, you minimize the number of local dependencies, you minimize the number of relations of C command, and no matter how deep is the structure, but you have to allow it to grow as much as it needs to. And this structure is, surprise, surprise, none other than the X-bar structure. This structure, well known to you. Okay. Now, an interesting aspect of this structure is that this can be something exactly like the four. This as a whole can be this, and then as a whole can be this. So you have something that you see highlighted here is the same structure repeated, and then you have first level of recursion, second level, third level, fourth level of recursion, and it can continue. Okay. So the winner is a minimax solution, as you have in physics, as you have in biology, as you have in neurobiology, I'll show you, and as you have in game theory. Don't have time to go into that, I mean much beyond. So the physics of minimax solutions, you have two conflicting forces, and you have to be composed, and you have a serial buildup of patterns, and what you have is the universe of relations that are the Fibonacci patterns. I will show you, for those who are not very familiar with that in a moment, various aspects of this nucleus of relation, mathematical relations. And you find them in organic structures, in plants, animals, in language, and even in galaxies. So this is the Fibonacci series. Each member is the sum of the previous two. And then very rapidly the ratio between two successive numbers converges to the golden section, approximately. It's a number that it continues to infinity, approximately 1.618. Here you have the bones of foot, but you find it all over the place. You have a Fibonacci sequence here. Here, this is the molecule of DNA. You have a larger groove and a smaller groove. The ratio between the size of the larger groove and the smaller grooves is the golden section. This is how you build the Fibonacci spiral via the Fibonacci series, and these are a few, just a few, of all the instances of the Fibonacci arrangements you find in nature. And what you find is not only Fibonacci structure, Fibonacci, but you find that the number, going in this direction, clockwise or counterclockwise, you have two Fibonacci numbers, 21 and 34, and so on and so on and so forth. The Fibonacci spirals all over the place. Now, this is a very fine article by two French physicists of a few years back, published in the Physical Review Letters, where you have the complete, total, all the equations and everything. So what you have here, you have drops of ferrofluid that fall onto a silica, dense medium, and they are attracted towards the circumference here, toward the side, and they repel each other. And after you let a certain number of drops fall, you see these very nice Fibonacci structures appearing. This is a perfectly inorganic, perfectly well-designed system. In fact, they published this as phyllotaxis, as a physical self-organizing growth process. You can find this on the internet in real time. It takes 5 or 6 minutes. I don't have the time to show you the movie. You see them being formed one after the other as the drops fall. Okay. Now, what you have here is that initially two successive drops depart one from the other at 180 degrees, but as you keep adding drops, very rapidly they converge onto the golden angle, 137.5. Very rapidly that happens. And here you have the Douadier-Couder pattern, and here you have one of the many manifestations of this pattern in biology. Many other examples. These are just a few. If you Google Fibonacci structures in biology, you find plenty. Asymmetry in the mammalian bronchial structure, consistent with the process of morphogenetic self-similarity described by Fibonacci scaling. The distribution of the frequency of bandwidths in EEG. I don't know why it's doing this. According to the Fibonacci-related golden mean, and they explain what you find in this paper of 2008, that you have a way to pack as many minimal interfering frequency bands as possible into the available frequency space. Now, Stuart Hameroff is a neuroscientist. He's the head of anesthesiology at the University of Arizona, and he came, Chomsky came in February. He gave a talk, and Stuart Hameroff was there, and he heard Chomsky say that syntax is basically a snowflake. He was absolutely delighted that he heard that the syntax is a snowflake, because he say we have the snowflakes, not syntax. They have snowflakes in the fundamental constitution of inside the neurons. And 3 days ago, this paper was published. You can find it on PLS Computational Biology. So here you have a complex, a molecular, indeed a snowflake. It looks like a snowflake. So this is a calcium calmodulin-independent protein kinase 2. And what you have here, it is a structure that is activated by the calcium influx, and then it's phosphorylated. These are the phosphorylated sites. So it is a structure that has 6 bits of information. And then when it is being phosphorylated, this you see from the front, this you see from the side. When it is phosphorylated, this is from the side. You have these little legs. You have these 6 legs that protrude down. And it is a very, very important, very frequent molecule. You find it all over the place in biology, in many signaling cascades, in calcium homeostasis, reuptake of cardiomyocytes. It's all over the place, positive T-cell selection, and so on and so forth. So these 6 legs match precisely the hexagonal lattice of microtubules. Microtubules are part of the skeleton of every cell. They are all over the place in every cell, but in neurons they have a particular lattice that they form, and the snowflake that you have seen, the calmodulin, adheres very precisely to the microtubules, and then you have long-term potentiation. You have, at the very least, memory. You can justify how memory can be formed and can be stabilized for so long, sometime during a whole lifetime, at a deeper level. Moreover, the grid cells in the entorhinal cortex, very, very important formation, interfering and communicating with the hippocampus, very, very important for the formation of memories and the formation of spatial maps, are separated, guess by what? By the golden mean, 1.618. So you have this molecule that you have seen a moment ago, which adheres, as is seen from the front, onto microtubules that are this hexagonal structure that can, in some cases, be many centimeters long. They can be fraction of a centimeter or many centimeters long. And what they do is they facilitate, these are tubulins, dimers of tubulins. The one that you see in dark, they are in an activated state, and there is a propagation of this activated state. This is a cellular automata, literally cellular automata, and they develop in their paper the theory. And lo and behold, what you find is that the propagation of information along the microtubules is the Fibonacci pathways, 853 from left. So you find them in the brain, you find these Fibonacci structures all over the place. Now, it has been shown a few years ago that if the dimers in these cytoskeletal microtubules forming a Fibonacci spiral, this gives the optimal way of transmitting and storing information. You couldn't do better than that. Okay? So they are cellular automata transmitting information. This is the physics we want now to find. This is, without going into the detail, you say that you have what you have is a fractal. You have something that repeats itself from times of the order of 10 seconds all the way down to terahertz. Okay? So you have scale-free dynamics from very, very small structure all the way up to whole neuron networks. It's very interesting. You have a fractal, you have something that is conserved across very, very interesting orders of magnitude. And here you have, this is, traditionally, Leonardo da Pisa, Filius Bonacci, known as Fibonacci, he had this curious idea of calculating how fast does a colony of rabbits reproduce. And he has this thing. So you have the twos are an adult reproductive pair, the one are a juvenile sterile pair. But let's forget about rabbits. This is the structure that he has discovered at the time. And now instead of rabbits, you have X bar, which is 2, and then you have X prime, the first projection, that is 1, and you have the Fibonacci series. So basically what you have in the Fibonacci string, instead of having the sum, the general formula is that each member is the sum of the previous two. Here what you have that each member is the concatenation of the previous two. And so you go to the Fibonacci string. Why is this Fibonacci string so interesting? This is the recipe, how you get it. If you see this, you substitute with 1. If you substitute with 1, 0, and so on and so on and so on. So you have the rule of continuation of the series is contained in the series itself. And you can regenerate the whole series from any part of it. So it is a fractal. So the golden tree is self-similar. Its linearization is also self-similar. So you have the property of self-similarity at many scales. Okay? Now, I hope you will hear, because I'm going to show you. So it is the simplest, most elegant fractal you can possibly have, because its fractal dimension is logarithm and base 2. This is what you want, and base 2 of phi, of the golden number. So the sequence encodes its very own procedure, and I hope you will hear now what an acoustic Fibonacci series sounds like. Now, this is extremely interesting because Doug Sadie at the University of Reading, already a couple of years ago, has tested adults with this sequence, the sequence you just heard, which is a Fibonacci sequence, with other 5 superficially, only superficially sounding like the sequence, but not being a Fibonacci sequence. And he says that now he's trying with children, he's trying electroencephalography and brain imaging. I don't have the data to report to you. But the data that I have, that he has already published, are these. So this is ease of memorization and ease of generalization. The gray bars are the Fibonacci. And these others in black are variants that superficially look like the Fibonacci, but are not. So they are better remembered, better generalized, and better processed. Now, it's very important. The Fibonacci sequence, as you see, has a lot of internal, sort of optimal internal structure. But it has no statistical regularity. I mean, if you have just heard 1, you don't know what is going to be the next 0 or 1. If you locally, just know, I heard 1, what I'm going to hear next is 50-50. So it has no local statistical regularity. So the facilitation that we have in memorizing and in extrapolating a Fibonacci series is not a statistical regularity. It's something much deeper and more interesting than just a statistical learning or statistical regularity. Bring this in mind. In the following days you will hear a lot about statistics, but bring in mind this, please. So these are found everywhere. Syllables, this is already goes back to Rhyme and Reason. Juan Uriagereka several years ago. Extension with Billy Sardi to prosody. Interesting have to do with words, but what for time constraints I will only go into syntactic structures. It goes also into the alternation between phases and non-phases. So this is the platoon of the crazy guys, of which I am one, I'm proud to be, who study Fibonacci structures in syntax. And as I said, it's just the beginning of something we think is really, really very interesting. So here you have the syntactic tree, and at all levels of the syntactic tree you have Fibonacci numbers. So this is the maximal projection, this is the first projection, this is the base, and you can continue and continue and continue. And what Dave Medeiros has shown, very interesting, is that an optimal tree. You couldn't do better than this. Also, he has this interesting theory that movement, syntactic movement, or copy deletion, if you prefer, is a tree balancing operation, is the best that you can possibly do. Also, if you keep adding terminals to a sentence in a syntactically legitimate way, you force a higher level of embedding if and only if you reach the next Fibonacci number. Okay? So here you have this structure, then you get the next Fibonacci number, and you have a higher level of embedding, and it can continue and continue and continue. Interesting property. Now, what are the interesting properties of what he has called the golden phrase, which is X bar? Well, there are 4 considerations. One consideration is that the simplest kind of syntactic binary multifractal. You cannot do better than that. It's the minimal semantic generator, the first shape to unlock the full set of predicate argument meanings. And then you have the specifier head complement order, yield string related to the golden string, infinite Fibonacci word. It has the lowest ambiguity among binary generators of binary. And finally, the mapping of hierarchy to linear order and its converse are straightforward, which is very important because we parse in real time, in a linear segment, but the hierarchy is what it is. So we go from the hierarchy to a linear sequence, and those who are listening to us go from the linear sequence to the hierarchy. Well, this mapping is absolutely perfect. You couldn't do better than that. It's really an optimal structure. Okay. Now, it seems to have to do with double articulation that has been evoked here earlier. So you have this potential of development on both sides, on 2 asymmetric sides. So you have something like barbarian destruction of Rome, and then you have the barbarian destroyed Rome, and then you have the phrasal off branches on both sides. It can be expanded. The ravening hordes of barbarian destroyed the gleaming city of Rome on the hill, and so on and so forth. So this arrangement has all these very, very nice properties. Now, C command, you are all familiar with C command, so you see even very, very simple structures like this, very simple trees, they have different numbers of relations of C command. And the hypothesis is that you want to minimize the number of C command relations. And you do this by moving things around so as to minimize the number of C command relations. You really want to have the minimum. And so you have a bushy structure like this is better than this because it minimizes the number of C command relations. And here you have how the number of C command relations grow as you grow more and more and more terminals. So you see that this is the spine. If you continue growing as a spine, they grow very fast. If you have the bush, it grows a lot less fast. So, it's much better to have this than to have this. And here you have, for the same radius, so to speak, the same number, it starts sort of low, and this is the total of possibilities, which already for radius 11, knots, you have 20,000, but then you continue, and here you have 27 million. And the number of solutions, of these solutions, is only a fraction, a tiny, tiny fraction of all the possibilities. So it makes a lot of sense that you have one of these very few possibilities instead of contemplating this monstrous number of what is only theoretically conceivable. Now, this is the fundamental movement condition that you have here. So here you have these two syntactic structures, and here you have this, the movement. This has moved here. What is the criterion? The criterion is basically that the number of nodes here multiplied by the distance by which you move must be greater than the number of what is left here. So here you have a couple of examples. You count the number of nodes here, and you have that this is okay. And also you have that if this is what happens, this is kind of movement you have, also you have that this is okay. So intuitively, you multiply the number of nodes in the moved structure by the overall distance moved, and it must be greater than the number of nodes in the unmoved tree, because then you make the calculation of all the C command relation, and you think this is exactly what you want. So movement is justified if and only if it balances the overall tree. The physics of language must have to do with balancing, must have to do with equilibrium. Okay, this is what we know from physics. So a small subtree moves far enough, or a larger tree moves only locally, always compensating for what is not moved. This is a very fine application that Dave Medeiros has developed of this idea that may sound not too abstract to a number of us. And you have Guglielmo Cinque's recent analysis of the possible orders in different languages of demonstrative, numeral, adjective, and noun. So in English, these four blind mice is perfect. Mice, these four blind is horrendous. Mice blind for this is horrendous. But in other languages, you have other orders. And this goes back to Greenberg, 1963, when he says when all of the items, demonstrative, numeral, and descriptive adjective precede the noun, they are always found in that order. If they follow, the order is either the same or its exact opposite. There was something right about this, but not quite right. And this is Cinque's summary of what you have in all languages that he has examined. He has examined many languages and dialect. So in white you have the attested orders, and in gray you have the unattested orders. So it's really different from what Greenberg had, okay, because Greenberg's generalization would have excluded this and would have allowed this. So this is the best that we have, and the explanation is exactly what Medeiros has supposed. Movement of the DP affects the NP, or an XP properly containing NP, no head or remnant movement, and so you have all the different possibilities under these following assumptions. You have the assumption of universality, that DP orders of every language represent transformation of a single common base structure. Coherence, they correspond to coherent subtrees, each one of them that cannot be broken apart further by movement. Monotonicity, all movement within the DP must satisfy the condition you have seen, the fundamental movement condition. And then continuity, every monotonic derivation corresponds to an attested order, and that is indeed the case. What now Dave Medeiros is doing is extending this kind of analysis also to verbs, to the organization of verbs. So you have modals, auxiliaries, verb, and particles, and it seems to work for those too. The data are not solid enough for me to project them to you. So these are just two examples. You have this order, and this is okay, and you have this order which is not okay, and then you compute, what you get here, you have an advantage, because you go from 124 C-command relation to 104, you diminish them, so it's great. Here you couldn't do this because you would be going from 114 C-command relation to 124. That is bad, that you don't want, so it is an order that is not attested. Here, by not going into the detail, this is Dave Medeiros has been calculating all the possibilities. So what you have in red here are movements that are forbidden. What you have in these black arrows, movements that are allowed. It is sort of a complete classification. Drives one crazy. He didn't drive him crazy. He has done this, and it is a summary of all movements that are allowed and movements that are not allowed. So what he has shown is that assuming that movement is for reducing the number of C-command relation, what you have is a single principle that accounts for the typology, at least, of DP orders, and we think that this is really in harmony with what we want in a syntactic inquiry, in a minimalist syntactic inquiry, because you are drawing accurate maps of syntactic structure and describing the constraint of movement within and across languages on the basis of a very, very simple physical, computationally optimal constraint. So all these strands are united in a single study. Patterns of movement, diagnose structure, and a structure determines possible movements. This looks to be very, very nice. Now, finally, notice the following. I said the physics of language. The physics of language, which is that you don't have, across all the things you have seen, all these different manifestations of Fibonacci structures, you keep finding them because the laws of nature apply. You do not keep finding them. A bit unlike what Stuart Hameroff was suggesting. You don't find them because there is a percolation of them all the way up, all the way down, or inheritance of one from the other. A laws of form, physical explanation, makes no claim of percolation, makes no claim that things filter down. It's a different kind of application. It's a different kind of explanation. It is reoccurring because the same principles apply again and again. And these principles are very simple, very elegant, very essential, parts of optimal computation, from physics to biology to language. So these are laws of minimalization that apply all the way up. And Feynman was right. This is interesting. Minimality principles are really interesting. And if one was bored by, whatever physics they were teaching him, if one was bored by, older ways of teaching language, perhaps one was right to be bored. Now you look at these things, and then this is, I think, fascinating, and it is the beginning of a kind of analysis that, for all its incompleteness and being still very tentative, I think points the way to something that we like, something that we think is a productive way of explaining things, not just positing them, but explaining as best we can on the basis of very fundamental physical principles. Thank you.